Hello there, and welcome back to Worlds Beyond Seen. Tonight, we're settling into something that sits at the very edge of science and mystery, a question that stretches across deep time and touches the lives of our ancient ancestors. What if, in the darkness before recorded history, the very poles of the Earth switched places? What if the compass that guides birds, whales, and wandering humans suddenly pointed the wrong way, or pointed nowhere at all? Before we begin this journey through time and magnetism, I'd like to invite you to like this video and subscribe to the channel. Your support helps us create more of these explorations into the mysteries of our world, and it means more than you might imagine. Tonight, we're going to ask a simple question with profound implications. What if Earth's magnetic poles flipped during human history? Not in some distant geological age when only bacteria witnessed the event, but during a time when our ancestors walked the Earth, when they huddled in caves, painted on walls, and watched the sky with wonder and fear. The truth is stranger than fiction. The poles have flipped, not just once, but hundreds of times throughout Earth's long history. And at least once, perhaps more, these reversals occurred while humans were very much present, watching, surviving, and perhaps recording what they saw in ways we're only now beginning to understand. So settle in, let your breathing slow. We're going to travel through time, through stone and ice, and ancient tree rings, to explore one of the most haunting possibilities in Earth science. That the chaos and darkness described in ancient legends might not be mythology at all, but memory. Distant, distorted memory of a time when the world's invisible shield faltered, when the sky lit up with auroras in places they should never appear, and when the very fabric of Earth's protective embrace grew thin and fragile. This is the story of magnetic reversals, ancient catastrophes, and the thin line between geological fact and human myth. The invisible shield, understanding Earth's magnetic field. We live our lives largely unaware of it. The magnetic field of Earth, that invisible bubble of force that wraps around our planet like a protective cocoon, exists beyond our senses. We can't see it, can't feel it, can't taste or smell or hear it, yet it's there, always, a guardian that has stood watch for billions of years. Think of Earth as a giant magnet, but not the simple bar magnet you might have played with as a child. This is something far more complex, far more dynamic, and infinitely more important to the survival of life as we know it. Deep within our planet, nearly 3,000 miles below your feet, lies the outer core. Here, in pressures and temperatures that would annihilate any substance we know from the surface world, liquid iron swirls and churns. This isn't a gentle stirring. This is a violent, roiling ocean of molten metal, heated to temperatures hotter than the surface of the sun, yet kept liquid by the crushing weight of everything above it. This iron ocean is in constant motion, driven by the residual heat left over from Earth's formation and the radioactive decay of elements deep in the planet's interior. As it moves, something remarkable happens. The flowing, electrically conductive iron generates electrical currents, and those currents, in turn, generate magnetic fields. These fields interact with each other, reinforcing and amplifying, creating a self-sustaining dynamo that has hummed away for over 3 billion years. The magnetic field that emerges from this deep engine extends far beyond the solid surface of our world. It reaches out into space, thousands of miles above your head, creating what scientists call the magnetosphere. This isn't just empty space with a slight magnetic tint. The magnetosphere is a battlefield, a zone of constant conflict between Earth's magnetic forces and the relentless assault of the solar wind. The sun, that bright disk in our sky that seems so benign, is actually hurling a continuous stream of charged particles into space at speeds of over 1 million miles per hour. These particles, mostly protons and electrons stripped from hydrogen atoms, would be deadly to life if they reached Earth's surface in their full fury. They would strip away our atmosphere molecule by molecule. They would bombard every living cell with radiation. They would, over time, turn Earth into a barren, lifeless rock like Mars, whose own magnetic field died billions of years ago. But Earth's magnetosphere deflects this solar wind, bending it around our planet like water flowing around a stone in a stream. Some particles do make it through, particularly at the poles, where the magnetic field lines dip down toward the surface. When these particles collide with oxygen and nitrogen in our upper atmosphere, they create one of nature's most beautiful displays, the Aurora borealis and Aurora australis, the northern and southern lights. For most of human history, these lights were confined to the far northern and far southern latitudes. The Inuit peoples of the Arctic, the Norse of Scandinavia, the inhabitants of Tasmania and southern Argentina, these were the cultures who regularly witnessed the dancing curtains of green and red light that rippled across their night skies. To them, the auroras were spirits, ancestors, omens, or gods at play. But what would it mean if those lights appeared where they shouldn't? What if auroras danced above Egypt, above central China, above the heart of Africa? What if the compass, that reliable tool that always points north, suddenly spun aimlessly, or worse, pointed south? This isn't hypothetical. This isn't science fiction. This has happened. The magnetic field of Earth is not constant. It wanders, it weakens, it strengthens, and sometimes, for reasons we still don't fully understand, it flips entirely. The north magnetic pole becomes the south magnetic pole. What was once a protective shield becomes, for a time, something more chaotic, something more dangerous. And the question that haunts us tonight is this: when it happened, were humans there to see it? And if they were, did it change them? Did it shape their cultures, their myths, their very understanding of reality? The magnetic poles are not the same as the geographic poles. The geographic poles, the points where Earth's axis of rotation intersects its surface, are fixed, or nearly so, with only minor wobbles. The magnetic poles, however, are restless wanderers. Right now, in our modern era, the North Magnetic Pole is racing across the Canadian Arctic towards Siberia at a pace of about 35 miles per year. This has accelerated dramatically in recent decades. In 1900, the North Magnetic Pole was firmly planted in northern Canada. By 2020, it had crossed the international dateline and was speeding through the Arctic Ocean toward Russia. This movement is normal. The liquid iron in Earth's core doesn't flow in neat, predictable patterns. It's turbulent, chaotic, full of eddies and currents that shift over time. As these patterns change, so does the magnetic field they generate. The poles drift, the field strength fluctuates, and magnetic north becomes a moving target. But drift is one thing, reversal is another. When scientists talk about a magnetic reversal, they mean something profound and unsettling. They mean a complete flip of Earth's dipole field. The field doesn't just weaken or shift slightly, it collapses, restructures, and emerges pointing the opposite direction. North becomes south, south becomes north. The compass that once pointed toward Polaris now points toward the constellation Octans. This isn't instantaneous. Earth isn't a light switch you can flip. A reversal is a process, and the process takes time. How much time? That's one of the great debates in paleomagnetism, the study of ancient magnetic fields. Some reversals might take just a few centuries, others might drag on for thousands of years. During this transition period, the magnetic field doesn't simply rotate in a neat, orderly fashion. It becomes weak, chaotic, unstable. Multiple magnetic poles might appear scattered across Earth's surface. The field might strengthen in one region while collapsing in another. The neat dipole pattern that we take for granted, with field lines arching gracefully from one pole to the other, fragments into a complex, ever-shifting patchwork of magnetic anomalies. And during this time of chaos, Earth's shield is down, not entirely gone, but greatly diminished. The magnetosphere shrinks, weakens, allows more solar wind and cosmic radiation to penetrate closer to the surface. This is when the auroras would spread. This is when the radiation would increase. This is when life on Earth, including any humans present, would face conditions unlike anything in their experience or their ancestors' memory. The evidence for past reversals is written in stone. Literally, when lava flows from a volcano and cools, iron-rich minerals within the rock align themselves with Earth's magnetic field, like tiny compass needles freezing in place. Once the rock solidifies, that magnetic signature is locked in, a fossilized snapshot of the direction and strength of the magnetic field at that moment in time. By sampling volcanic rocks of different ages from around the world, scientists have reconstructed the history of Earth's magnetic field, stretching back hundreds of millions of years. What they found astonished them. Reversals are common, not frequent on human timescales, but common in geological time. Over the last 83 million years, there have been at least 183 reversals. That's an average of one every 450,000 years or so. Some periods see reversals happen more frequently, clustering together like a rapid-fire sequence of magnetic storms. Other periods, like the one we call the Cretaceous normal superchron, see no reversals at all for tens of millions of years. The most recent full reversal, the one that set our current magnetic configuration, happened about 780,000 years ago. This event is called the Brunhes-Matuyama reversal, named after the geophysicists who first identified it. Before that reversal, your compass would have pointed south, after it, north. But 780,000 years ago is deep in the Pleistocene, long before modern humans existed, long before Homo sapiens walked out of Africa. If we're asking whether a reversal happened during human history, we need to look more closely at the geological record. And here, the story becomes more interesting and more controversial, because while full reversals are rare, there's another type of magnetic event that happens more frequently. These are called excursions. During an excursion, the magnetic field weakens dramatically. The poles might shift significantly or even temporarily reverse, but then the field recovers and returns to its original polarity. Think of it as the magnetic field attempting to flip, struggling with the process, and then giving up and reverting to its previous state. Excursions are shorter than reversals, typically lasting a few hundred to a few thousand years rather than tens of thousands. But during that brief window, the effects on Earth's surface could be just as dramatic. And there's one excursion in particular that has captured the attention of scientists, storytellers, and anyone who wonders about the hidden forces that shaped our ancestors' world. It's called the Lachamp excursion, and it happened approximately 42,000 years ago. At that time, modern humans had already spread across much of Africa, Europe, and Asia. Neanderthals still existed, though they were in decline. Cave art was being created, tools were being refined, language, culture, and society were developing, and the magnetic field of Earth was about to do something extraordinary. The science of pole reversals, when north becomes south. Let's slow down for a moment and really understand what a magnetic reversal means, not just as an abstract concept, but as a physical process that unfolds in the deep interior of our planet and radiates its effects across the entire world. Imagine you could somehow journey to the center of Earth. You descend through the rocky crust, through the solid mantle with its slow convection currents, and finally reach the outer core, a sphere of liquid iron and nickel roughly the size of Mars, spinning and churning in the darkness. This is no calm ocean. The outer core is driven by powerful forces, the cooling and crystallization of the inner core, which releases heat and lighter elements, the residual primordial heat from Earth's formation, and the decay of radioactive isotopes scattered throughout the deep interior. These forces drive convection, creating massive currents of molten metal that flow at speeds of millimeters per second, which might not sound like much, but when you're talking about volumes of metal measured in cubic kilometers, those millimeters add up to titanic forces. As this electrically conductive fluid moves through any existing magnetic field, it generates electrical currents through a process called induction. Those currents, in turn, generate their own magnetic fields. If the geometry is right, if the currents flow in certain patterns, they can reinforce the existing magnetic field, making it stronger. This is the geodynamo, Earth's self-sustaining magnetic generator, but it's a delicate balance. The outer core is turbulent, chaotic, Small changes in flow patterns can have large effects. Computer simulations of the geodynamo show that the magnetic field is constantly shifting, strengthening in some regions, weakening in others, its poles drifting across the surface in response to changes in the underlying flow. Most of the time, these shifts are minor. The field remains stable in its overall configuration, a dipole with north and south poles, strong and protective, keeping Earth safe. But occasionally, something changes. Perhaps it's a particularly strong eddy in the outer core. Perhaps it's a change in the way the inner core is crystallizing. Perhaps it's the accumulation of many small perturbations that finally push the system past some tipping point. Whatever the trigger, the result is the same. The magnetic field begins to weaken. Its dipole character starts to break down. Patches of reverse polarity appear at the surface, growing and spreading like cracks in ice. During the transition, Earth's magnetic field doesn't vanish, but it becomes much weaker and much more complex. Instead of a single North Pole and South Pole, there might be multiple poles scattered across the globe. The field lines, instead of arcing neatly from pole to pole, become tangled and chaotic. This is the danger zone. This is when Earth's protective shield is at its lowest ebb. The magnetosphere, that bubble of magnetic force that normally extends tens of thousands of miles into space, shrinks dramatically. In some simulations, it retreats to just a few Earth radii above the surface. Solar wind and cosmic radiation, which normally are deflected far from Earth, now penetrate much closer. More particles reach the upper atmosphere. More energy is deposited at lower latitudes. The aurora zones, normally confined to rings around the magnetic poles, expand dramatically. Auroras might be visible from the equator, and it's not just the pretty lights that change. The increased radiation in the upper atmosphere affects atmospheric chemistry. More ionization occurs, creating more of certain isotopes like carbon-14 and beryllium-10. These isotopes get incorporated into living things, into ice, into sediments, leaving a signature that can be detected tens of thousands of years later. The increased radiation might also affect the ozone layer, that thin protective veil in the stratosphere that shields the surface from harmful ultraviolet light. Some climate models suggest that during a reversal or excursion, the ozone layer could thin significantly, allowing more UV radiation to reach the surface. What would this mean for life on Earth? For most organisms, probably not much. Evolution has equipped life with remarkable resilience. DNA repair mechanisms can handle moderate increases in radiation. Most species would adapt, shelter, or simply endure. But for a species that had recently evolved intelligence, that was beginning to rely on complex social structures and cultural transmission of knowledge, even moderate environmental stress could have significant effects. Increased UV radiation might force people to seek shelter more often, to cover their skin, to avoid certain times of day. Increased auroras might inspire awe, fear, or religious experiences. Changes in the behavior of migratory animals, which use Earth's magnetic field for navigation, might affect hunting success. And if the reversal happened quickly enough, if it happened within a few human generations rather than over thousands of years, it might be noticed, it might be remembered, it might be passed down in stories, in myths, in the collective memory of a culture trying to make sense of a world that had suddenly and inexplicably changed. The geological evidence tells us that reversals do happen, have always happened, will likely happen again. The average time between reversals is about 300,000 to 400,000 years. Our current magnetic polarity has lasted for 780,000 years, nearly twice as long as average. By that logic, some scientists argue we're overdue for a reversal. But overdue is a misleading term. Reversals aren't governed by a clock. They're governed by the chaotic dynamics of Earth's core, and chaos, by definition, isn't predictable. The next reversal might start tomorrow, or it might not happen for another million years. There's simply no way to know. What we can say with confidence is this: reversals happen, they've happened throughout Earth's history, and they've happened at least once, maybe more, during the time that human beings have existed on this planet. The question is, what did it do to us? A timeline of magnetic reversals, when the poles danced. Let's step back and look at the big picture, the long view of Earth's magnetic history. If we could watch a time-lapse of our planet's magnetic field spanning hundreds of millions of years, we'd see something that looks almost alive. The poles would drift slowly across the surface, wandering like restless ghosts. Then, every few 100,000 years, the field would flicker, weaken, and snap into a new configuration with the poles reversed. This magnetic wandering has been going on for as long as Earth has had a liquid outer core, which is to say, for most of the planet's 4.5 billion year history. During the Precambrian, over 500 million years ago, reversals happened frequently, sometimes multiple times per million years. The Paleozoic era, the age of early complex life, saw its share of reversals, though the details are harder to reconstruct from rocks that ancient. The Mesozoic era, the age of dinosaurs, had an interesting quirk. For about 40 million years during the Cretaceous period, from roughly 121 to 83 million years ago, Earth's magnetic field was stable. No reversals, no excursions, just a steady, strong dipole field. This period is called the Cretaceous normal superchron, and it remains one of the great mysteries of geomagnetism. What kept the field so stable for so long? Was it something special about the state of the core at that time? We don't know. But then, after that long, quiet period, reversals resumed. The Cenozoic era, our current era, the age of mammals, and eventually humans, has seen reversals return to their more typical pattern, occurring every few 100,000 years on average. The most recent full reversal, as we've mentioned, happened 780,000 years ago. That's the Brunhes-Matuyama reversal. Before that, the Matuyama reversed epoch lasted from about 2.6 million to 780,000 years ago. Before that, the Gauss normal epoch, and so on back through time. These epochs are named after scientists who made significant contributions to the study of paleomagnetism: Brunhes, Matuyama, Gauss, Gilbert. The epochs themselves are identified by studying the magnetic signature locked into volcanic rocks and ocean floor sediments. The ocean floor, in particular, provides a beautiful record of magnetic reversals. As new oceanic crust forms at mid-ocean ridges, magma wells up from below, cools, and solidifies. The iron minerals in the rock align with Earth's magnetic field at that moment. As the seafloor spreads away from the ridge, it carries that magnetic signature with it, like a tape recorder, preserving a record of the field's polarity. When scientists mapped the magnetic patterns on the ocean floor in the 1,960 seconds, they found something extraordinary: a striped pattern of normal and reversed magnetic zones running parallel to the mid-ocean ridges. These stripes were symmetrical on both sides of the ridge, proof that new crust was forming at the center and spreading outward. This discovery was one of the key pieces of evidence for plate tectonics, revolutionizing our understanding of how Earth's surface evolves over time. But for our purposes tonight, the ocean floor magnetic stripes are important because they give us a clear, continuous record of reversals going back tens of millions of years. By measuring the width of the stripes and knowing the spreading rate, geologists can calculate how long each polarity interval lasted. What they found is that reversals are random, or at least appear to be. There's no regular pattern, no predictable cycle. Some normal epochs last a few 100,000 years, others last millions of years. The same is true for reversed epochs. And in between these major reversals, there are shorter events, the excursions. Excursions are harder to detect in the geological record because they're brief, and because the magnetic signature might not be preserved as clearly as a full reversal. But as dating techniques have improved and more sites have been studied, scientists have identified dozens of excursion events spanning the last million years. Some of these excursions have names: the Blake event, around 120,000 years ago; the Jamaica event, around 200,000 years ago; the Mono Lake event, around 34,000 years ago; and perhaps the most famous and most studied of all, the Lachamp event, approximately 41,000 to 42,000 years ago. Each of these events represents a time when Earth's magnetic field weakened and became unstable, when the poles wandered far from their usual positions, when the protective magnetosphere thinned and allowed more radiation to reach Earth's surface. And each of these events occurred during the Pleistocene, or early Holocene, during the time when anatomically modern humans were spreading across the globe, when archaic humans like Neanderthals and Denisovans still existed, when our ancestors were living in a world shaped by ice ages and megafauna. This is where the story gets interesting for those of us curious about the intersection of geology and human history, because while full reversals might be too rare to have occurred during the span of human existence, excursions are much more common, and at least one, the Lachamp, occurred during a crucial period in human prehistory. But before we dive deep into the Lachamp event and its potential effects on ancient humans, we need to ask a broader question. If a major geomagnetic event happened during human history, would we expect to see evidence for it in the archaeological record? In human genetics? In myths and legends? This is where science meets speculation, where data meets story, and where we begin to ask uncomfortable questions about how much we really know about our past. Ancient civilizations and geomagnetic events, the archaeological record. When archaeologists excavate ancient sites, they're looking for artifacts, structures, bones, the tangible remnants of past lives. They can tell you what people ate, what tools they used, how they buried their dead, sometimes even what diseases they suffered from. But can they tell you if the people at that site experienced a geomagnetic excursion? Can they identify the signature of a weakened magnetic field in the archaeological record? The answer is complicated. Let's start with what archaeologists can measure directly. When ancient humans built fires, whether for cooking, warmth, or pottery making, the heat affected the magnetic properties of the soil and rocks nearby. Iron oxide minerals in the ground, when heated above a certain temperature called the Curie point, around 580 degrees Celsius for magnetite, lose their magnetic orientation. Then, as they cool, they realign with whatever magnetic field is present at that moment. This process, called the permanent magnetization, effectively records a snapshot of Earth's magnetic field direction and intensity at the time the fire cooled. By carefully sampling and analyzing these ancient hearths and kilns, archaeomagnetists, yes, that's a real specialty, can reconstruct what Earth's magnetic field was doing thousands of years ago. Archaeomagnetism has revealed that Earth's magnetic field has been quite variable over the past few thousand years. The magnetic North Pole has wandered considerably. The field strength has fluctuated. There have been periods when the field was significantly weaker than it is today, and periods when it was stronger, but detecting a full excursion or reversal in the archaeological record is much harder. For one thing, most archaeological sites don't provide continuous records spanning thousands of years. There might be layers representing different occupations separated by centuries or millennia. For another, the dating precision required to correlate archaeological features with specific geomagnetic events is challenging to achieve. Still, there are hints, tantalizing suggestions, that major geomagnetic events might have left their mark on human societies. Consider the distribution of archaeological sites and cultural changes around 42,000 years ago, the time of the Lachamp excursion. This is the beginning of the Upper Paleolithic in Europe, a time of significant cultural transformation. We see the appearance of more sophisticated stone tools, the first undisputed evidence of cave art, the use of bone and antler for tools and ornaments, and evidence for long-distance trade networks. In a 2021 paper published in the journal Science, a team of researchers led by Alan Cooper suggested that the Lachamp event might have played a role in driving some of these changes. They argued that the weakened magnetic field during the excursion would have allowed more cosmic radiation to reach Earth's surface, potentially affecting climate, causing increased UV radiation, and creating environmental stresses that forced human populations to adapt. The paper was titled a global environmental crisis 42,000 years ago, and it created quite a stir in both the scientific community and the popular press. The researchers dubbed this period the Adams Event, a tongue-in-cheek reference to Douglas Adams' Hitchhiker's Guide to the Galaxy, which famously claimed that 42 was the answer to the ultimate question of life, the universe, and everything. The Cooper team's argument went something like this. During the Lachamp excursion, Earth's magnetic field dropped to as low as 6% of its current strength for a period of several centuries. This weakening, combined with a period of low solar activity, a grand solar minimum, would have dramatically increased the amount of cosmic radiation reaching Earth's atmosphere. More cosmic rays means more production of cosmogenic isotopes like carbon-14 and beryllium-10. The researchers found evidence for this spike in ancient tree rings from New Zealand kauri trees that lived through the event. More cosmic rays also means more ionization in the upper atmosphere, which could affect the ozone layer, allowing more UV radiation to reach the surface. The modelling done by Cooper's team suggested that the combination of weakened magnetic field and solar minimum could have caused significant climate disruptions, changes in atmospheric circulation patterns, increased auroras at low latitudes, more lightning storms, and ozone depletion. They then pointed to various events in the archaeological and paleontological record around this time. The extinction of Australian megafauna, the disappearance of Neanderthals from Europe, the appearance of red ochre in cave paintings, which they speculated might have been used as a kind of primitive sunscreen, and major shifts in human behaviour. The paper was bold, provocative, and immediately controversial. Critics pointed out several problems with the hypothesis. First, the archaeological and paleontological changes cited in the paper don't all date precisely to 42,000 years ago. The extinction of Australian megafauna, for instance, is now thought to have occurred over a much longer period, with some species surviving well past 42,000 years ago. The disappearance of Neanderthals from Europe was a gradual process spanning thousands of years, and had likely already begun before the Lachamp event. Second, the climate effects predicted by the modelling are not strongly supported by ice core records from Greenland and Antarctica, which don't show dramatic climate changes at 42,000 years ago. If there was a global environmental crisis, it should show up in these records, and it doesn't, at least not obviously. Third, humans and other species had survived previous geomagnetic excursions without any clear signs of mass extinction or cultural upheaval. The Blake excursion, for instance, occurred around 120,000 years ago, and there's no evidence that it caused any major problems for Neanderthals, Homo sapiens, or megafauna. And finally, the increases in cosmic radiation predicted by the models, while measurable, are relatively modest. Earth's atmosphere is a powerful shield against radiation even without a strong magnetic field. For the radiation to have significant biological effects, the exposures would need to be much higher than what's predicted. So, where does that leave us? The honest answer is, we don't know for certain. The Lachamp event definitely happened. The magnetic field definitely weakened. The amount of cosmic radiation reaching Earth definitely increased. These are facts, supported by multiple lines of evidence. But whether these changes were severe enough to cause a global environmental crisis, to drive extinctions, to fundamentally alter human behaviour, that remains an open question. The correlation between the Lachamp event and various archaeological and paleontological changes is intriguing, but correlation doesn't prove causation. It's possible that the Lachamp event was just one of many stressors affecting human and animal populations at that time. Climate change, driven by orbital cycles, the Milankovitch cycles, was ongoing. Humans were expanding into new territories, competing with established species. Megafauna populations might have been declining due to hunting pressure or habitat changes. In this view, the Lachamp event might have been the straw that broke the camel's back, an additional stress on top of existing pressures, rather than the sole cause of major changes. Or it's possible that the effects of the Lachamp event were real but subtle, influencing human behaviour in ways that left traces in the archaeological record, but which are hard to definitively link to the geomagnetic changes. For instance, increased auroras at low latitudes might have inspired awe and fear, leading to changes in religious practices or migration patterns. These changes would be visible in the archaeological record: new types of sites, new artifact styles, evidence for movement, but it would be extremely difficult to prove that they were caused by the auroras rather than by other factors. What we can say is this: around 42,000 years ago, human populations were experiencing significant changes. New technologies were emerging. Art was becoming more sophisticated, long-distance networks were forming, and at the same time, Earth's magnetic field was doing something unusual. Whether these two things are connected is a question that will require more research, better dating techniques, and probably a good deal of creative thinking about how to test hypotheses about events that happened in the deep past. But the question itself is valuable. It forces us to think about human history not just in terms of cultural and technological evolution, but also in terms of the physical environment, including forces like the magnetic field that are usually invisible and taken for granted. Our ancestors didn't live in a static world. They lived on a dynamic planet, a planet that was constantly changing in ways both large and small, and one of the most fundamental of those changes was the behavior of the magnetic field itself. Legends, myths, and oral traditions, echoes of chaos. Now let's turn to something more speculative, but equally fascinating. What if ancient myths and legends preserve memories, however distorted, of geomagnetic events? Human cultures have always tried to explain the world around them through stories. These stories serve multiple purposes. They teach moral lessons, they explain natural phenomena, they bind communities together through shared narratives, and they preserve important information across generations. In pre-literate societies, oral tradition was the only way to transmit knowledge. Stories were memorized, recited, adapted, and passed down from parent to child, from elder to youth, across centuries and millennia. Some of these stories are remarkably persistent. Australian Aboriginal oral traditions, for instance, have been shown to preserve accurate information about coastal geography from before the end of the last ice age, over 10,000 years ago. Stories describe islands that are now submerged, bays that are now filled in, shorelines that have moved dramatically as sea levels rose. If oral traditions can preserve geographical information for 10,000 years, might they also preserve information about unusual events in the sky, about periods of darkness, chaos, or strange lights? Let's consider what ancient people might have observed during a geomagnetic excursion like the Lachamp event. First, the auroras. Normally confined to high latitudes, auroras during an excursion would expand dramatically toward the equator. People living in places that never normally saw auroras, places like North Africa, the Middle East, Central Asia, even the tropics, might suddenly witness shimmering curtains of light dancing across their night skies. These lights would be unlike anything in their experience. They might be interpreted as spirits, as gods, as omens, as the fabric of the sky tearing open. Different cultures would give them different meanings, but all would agree something strange and powerful was happening. Second, navigation. Many animals use Earth's magnetic field to navigate, including birds, sea turtles, salmon, and even some insects. If the magnetic field became chaotic, with multiple poles, or with the poles wandering rapidly, these animals would become disoriented. Birds might fly in strange directions, fish might fail to return to their spawning grounds. This disruption in the natural order would be noticed by human hunters and fishers, who depended on the predictable behavior of their prey. Third, increased radiation. While the direct biological effects of increased cosmic radiation during an excursion might be modest, there could be indirect effects. Increased ionization in the atmosphere might lead to more lightning storms, more dramatic cloud formations, unusual atmospheric electrical phenomena like Street Elmo's fire. The thinning of the ozone layer might lead to more intense sunlight, more sunburns, forcing people to cover their skin or seek shade more often. Fourth, climate changes. If the geomagnetic excursion coincided with or contributed to changes in atmospheric circulation or ocean currents, there might be shifts in local weather patterns, droughts where there was once rain, cold snaps in normally mild regions, unusual storms. Any or all of these effects might find their way into myths and legends, encoded in symbolic language that later generations would struggle to interpret. Consider flood myths. Nearly every culture on Earth has a flood myth. The biblical Noah's Ark, the Mesopotamian epic of Gilgamesh, the Hindu Matsya Purana, the Chinese Gunyu flood, the Greek myth of Deucalion, indigenous Australian Dreamtime stories, Native American legends. The details vary, but the theme is consistent: a catastrophic flood that destroys the world, with only a few survivors. Most scholars attribute these myths to memories of local or regional floods, combined with the near-universal human experience of seeing rivers overflow and imagining what would happen if the waters just kept rising. The global end of Ice Age sea level rise, which drowned coastal areas around the world between 20,000 and 7,000 years ago, might also be preserved in these stories. But could some flood myths contain distorted memories of other catastrophes? Could storms driven by a weakened magnetic field, or climate changes triggered by an excursion, have caused flooding that seemed world-ending to the people who experienced it? Consider darkness myths. Many cultures have myths about a time when the sun disappeared, or when the world was plunged into darkness. In Norse mythology, there's the Fimbul winter, a great winter that precedes Ragnarok, a time when the sun and moon are swallowed by wolves, and the world is cast into darkness and cold. In some Native American traditions, there are stories of a time when the sun failed to rise, or when the stars fell from the sky. Could these myths preserve memories of a time when volcanic eruptions, meteor impacts, or atmospheric changes caused by a geomagnetic event dimmed the sun or obscured the stars? Consider myths about the sky changing. In some traditions, there are stories about a time when the sky was different, when the stars moved in strange ways, when new lights appeared. The Hopi people of North America have traditions about sky people and about times when the stars told stories that are now forgotten. Many cultures have myths about the sky falling or the pillars of heaven being disturbed. Could these reflect observations of auroras in unexpected places, of the sun and moon following slightly different paths due to the wandering of the magnetic poles, which would affect compass-based navigation and might have been interpreted as the celestial bodies themselves moving differently? The challenge with interpreting myths is that they're symbolic, not literal. They've been embellished, adapted, merged with other stories over countless retellings. Separating the historical kernel, if there is one, from the symbolic overlay is extremely difficult. But that doesn't mean we should dismiss myths entirely. They might not give us precise dates or scientific measurements, but they can give us something else, a sense of how ancient people experienced and interpreted unusual events. If a geomagnetic excursion caused widespread auroras, our ancestors wouldn't have understood what they were seeing in terms of magnetic fields and solar particles, but they would have known that something was wrong, that the sky was behaving in ways it shouldn't, that the natural order had been disrupted, and they would have told stories about it. They would have created rituals to appease whatever gods or spirits they thought were responsible. They would have passed these stories down, and over time, the stories would change, would merge with other stories, would become myth. So when we find myths that talk about chaos in the sky, about darkness and strange lights, about the world turning upside down, it's worth asking, might these preserve some echo, however faint, of real events that our ancestors witnessed? The answer, frustratingly, is maybe. Without clearer correlations between specific myths and specific geomagnetic events, without better dating of when myths originated, which is nearly impossible for oral traditions, we can't be certain. But the possibility remains tantalizing. Perhaps our myths are not entirely fiction. Perhaps they contain fragments of memory from a time when Earth's shield failed, when the sky lit up with impossible colors, when the world seemed to be ending, And perhaps, buried in those old stories, there are clues that could help us understand what really happened during the Lachamp event and other geomagnetic excursions that punctuated human prehistory. Archaeological evidence and anomalies. Reading the stones. Let's return to harder evidence, to the things we can measure and test. If a geomagnetic excursion affected ancient human populations, we should be able to see evidence for it in the archaeological record, not necessarily in myths or stories, but in the physical remains of past lives, in the distribution of sites, in changes in artifact styles, in evidence for migration or cultural disruption. So what does the archaeological record show? The period around 40,000 to 42,000 years ago is a fascinating time in human prehistory, particularly in Europe. This is the transition from the Middle to Upper Paleolithic, a time when Neanderthals were disappearing and modern humans were expanding into new territories. The Middle Paleolithic, dominated by Neanderthals in Europe and by various archaic humans elsewhere, was characterized by a particular style of stone tool technology called Mousterian. Mousterian tools are well made, functional, but relatively standardized and unchanging over long periods. Then, around 45,000 to 40,000 years ago, depending on the region, we start seeing new technologies appearing. The Upper Paleolithic is marked by a proliferation of tool types, much greater use of bone and antler, the appearance of personal ornaments, beads, pendants, and the first clear evidence for cave art and portable art objects. This transition doesn't happen overnight. There's a period of overlap where Neanderthal and modern human populations coexisted, sometimes in the same regions. There are even some transitional industries, like the Châtelperronian in France and the Uluzzian in Italy, which show a mix of Middle and Upper Paleolithic traits and might represent Neanderthals adopting some modern human technologies. Eventually, though, the Neanderthals disappear from the fossil and archaeological record. The last secure dates for Neanderthal sites are around 40,000 years ago, with a few controversial later dates that are still debated. So we have this picture, a period of cultural change, population movements, and the extinction of an entire human species, all happening roughly around the time of the Lachamp excursion. Correlation? Maybe. Causation? Much harder to prove. Let's look at the arguments for a connection. First, the timing. The Lachamp excursion is dated to approximately 41,000 to 42,000 years ago, based on multiple lines of evidence, including volcanic rocks, sediment cores, and tree ring records. The final disappearance of Neanderthals from Europe is dated to around 40,000 years ago. The emergence of cave art and sophisticated Upper Paleolithic technologies happens around the same time. If these events are all happening within a few thousand years of each other, it's natural to ask whether they're related. Second, the environmental context. Neanderthals had survived multiple glacial cycles, multiple climate changes, over hundreds of thousands of years. They were well adapted to cold environments. What finally pushed them to extinction? The standard explanation is competition with modern humans, who had certain advantages: better long-range weapons, more sophisticated social networks, possibly better language abilities. Modern humans simply outcompeted Neanderthals for resources until Neanderthal populations dwindled and disappeared. But could environmental stress from the Lachamp event have played a role? If the weakened magnetic field caused climate changes, if it led to increased radiation and ozone depletion, Neanderthal populations that were already under pressure from modern human expansion might have been pushed past the tipping point. Third, the appearance of cave art. The oldest known cave paintings in Europe, like those in Chauvet Cave in France and El Castillo Cave in Spain, date to around 40,000 to 35,000 years ago. Earlier examples of symbolic behavior exist: shell beads, ochre use, but monumental cave art seems to appear suddenly during the Upper Paleolithic. Why? What inspired these early artists to venture deep into caves and create these masterpieces? One speculative idea, proposed by some researchers, is that increased auroras during the Lachamp event might have inspired a sense of the supernatural, a feeling that the sky was full of spirits or gods. This might have led to increased ritual behavior, including the creation of sacred art in caves, which themselves might have been seen as gateways to the underworld or spirit realm. This is, admittedly, highly speculative. There's no direct evidence linking cave art to auroras or to geomagnetic events, but it's an interesting idea, and it reminds us that ancient people's motivations and inspirations were shaped by their environment in ways we might not fully appreciate. Fourth, the use of red ochre. Many Upper Paleolithic sites, especially those associated with the earliest cave art, show extensive use of red ochre, a pigment made from iron oxide. Ochre is used to colour artifacts, to paint cave walls, and sometimes to cover human burials. The Cooper et al. Paper suggested that increased use of ochre might have been a response to higher UV radiation during the Lachamp event. Ochre could have served as a primitive sunscreen, protecting skin from sunburn. This idea has been met with skepticism. While it's true that some mineral pigments can block UV radiation, it's not clear that ochre was being used for this purpose. People might have valued ochre for its colour, for its symbolic associations with blood or fire, for its use in rituals. Suggesting that it was practical sunscreen seems like a stretch. Still, the timing is interesting. If people were experiencing more intense sunlight due to ozone depletion, they might have noticed that covering their skin with certain substances, ochre, clay, fat, provided some protection, even if they didn't understand why. Fifth, evidence for migration. Around 40,000 years ago, there's evidence for human populations moving into new areas, including regions that had previously been occupied by Neanderthals. Some of this is clearly just the expansion of modern human populations as they spread out of Africa and into Eurasia. But could environmental changes driven by the Lachamp event have made some regions less habitable, forcing populations to move? Again, this is hard to prove. Migration can be driven by many factors: climate change, resource availability, population pressure, technological innovations that make new environments accessible. Teasing apart the relative importance of these factors is extremely difficult. So, when we look at the archaeological record from around 40,000 to 42,000 years ago, we see a lot of interesting things happening. Cultural changes, population movements, extinctions, the emergence of new behaviours. But we can't definitively say that these were caused by the Lachamp excursion. What we can say is that the correlation is intriguing and worth further investigation. As dating techniques improve, as we get more archaeological data from more sites around the world, as we develop better climate models that can predict the effects of geomagnetic excursions, we might be able to test these hypotheses more rigorously. For now, the jury is out. The Lachamp event happened. It was a significant geomagnetic event. Whether it was also a significant event in human history remains an open question. The Lachamp event, a case study in ancient magnetic chaos. Let's focus in now on the Lachamp excursion itself, the best studied geomagnetic event to occur during the existence of modern humans. What exactly happened during the Lachamp event? How do we know, and what can it tell us about what might happen during future geomagnetic disturbances? The Lachamp excursion is named after a small village in the massive central region of France, near Clermont-Ferrand. In the 1960 seconds, geologists studying ancient lava flows in the area discovered something strange. The rocks were magnetized in the wrong direction. Instead of aligning with the current magnetic field pointing north, the magnetic minerals pointed south. This was the first clear evidence of the Lachamp excursion, though at the time, scientists didn't fully understand what they had found. Was this a full reversal? A brief anomaly? How long had it lasted? When exactly had it occurred? Over the following decades, as more sites were studied and dating techniques improved, a clearer picture emerged. The Lachamp event was not a full permanent reversal, but an excursion, a temporary flip that lasted a few hundred years before the magnetic field returned to its original polarity. The event has now been identified at sites all over the world, in volcanic rocks from Iceland, Italy, New Zealand, and the western United States, in sediment cores from the North Atlantic, Pacific, and Indian Oceans, in ice cores from Greenland and Antarctica, and most recently, in the growth rings of ancient trees. The most detailed record of the Lachamp event comes from a remarkable discovery in New Zealand. In 2019, workers preparing ground for a power plant near the town of Ngava unearthed the massive trunk of an ancient kauri tree, Agathis australis, one of the largest tree species in the world. The trunk, preserved in a swamp for over 40,000 years, was enormous, 60 tons of ancient wood, perfectly preserved. When scientists examined the tree, they realized they had something extraordinary. The tree had lived for approximately 1,700 years, and its growth rings spanned the entire Lachamp excursion. Tree rings are like time capsules. Each ring represents 1 year of growth, and the wood preserves a chemical record of atmospheric conditions during that year, including the levels of radioactive carbon-14. Carbon-14 is produced when cosmic rays from space collide with nitrogen atoms in Earth's upper atmosphere. Under normal conditions, with a strong magnetic field, Earth's magnetosphere deflects most cosmic rays, so carbon-14 production is relatively constant. But during a geomagnetic excursion, when the magnetic field weakens dramatically, more cosmic rays penetrate to the atmosphere, and carbon-14 production increases. By measuring carbon-14 levels in the kauri tree rings, scientists could reconstruct changes in Earth's magnetic field strength with unprecedented precision. What they found was startling. Leading up to the Lachamp event, Earth's magnetic field was already weakening. Then, starting around 42,300 years ago, the field collapsed to just 6% of its current strength. 6%. That's barely a shield at all. During this time, the magnetic poles didn't just drift, they wandered dramatically. The North Magnetic Pole swung across North America, out toward the Atlantic, down through the Pacific, hovered near Antarctica for a time, then shot back up through the Indian Ocean. This wasn't an orderly reversal. This was chaos. Multiple magnetic poles appeared at different locations. The field lines became tangled and confused. For a period of several centuries, any compass would have been useless, spinning erratically or pointing in seemingly random directions. Then, around 41,500 years ago, the field began to recover. It strengthened, the poles settled back toward their original positions, and within a few hundred years, the excursion was over. Earth's magnetic field was back to its normal configuration, as if nothing had happened. But something had happened. For those few centuries, Earth's shield was down. The magnetosphere shrank to a fraction of its normal size. Cosmic rays flooded into the atmosphere in unprecedented numbers. Auroras blazed across the sky at latitudes that normally never saw them. The amount of radiation reaching the surface increased significantly. How much radiation? This is where the models come in. Scientists used the carbon-14 data from the tree rings, combined with ice core records and sediment data, to estimate cosmic ray flux during the Lachamp event. Their models suggest that cosmic ray intensity increased by about 190% compared to normal levels. That might not sound like much, but remember, we're talking about energetic particles from space. Even a modest increase can have effects on the atmosphere. The increased cosmic rays would produce more ionization in the upper atmosphere, creating more of certain chemical species, affecting atmospheric chemistry and potentially thinning the ozone layer. Some models suggest that ozone levels could have dropped by as much as 3 to 6% globally, with larger decreases at high latitudes. A 6% decrease in ozone translates to a roughly 15 to 20% increase in UVB radiation reaching the surface. That's enough to cause noticeably more sunburns, skin damage, and potentially eye damage. The increased cosmic rays would also produce more nitrogen oxides in the upper atmosphere, which are greenhouse gases. This could lead to some warming, though the effect would be relatively small compared to natural climate variability. More speculatively, the increased ionization could affect cloud formation. Cosmic rays help seed clouds by ionizing air molecules, which can then act as condensation nuclei. More cosmic rays might mean more clouds, which would reflect sunlight and cool the surface. But this effect is highly uncertain and controversial. The Cooper et al. Team also considered another factor: solar activity. Around the time of the Lachamp event, the Sun appears to have entered a period of low activity called a grand solar minimum. We know this because levels of certain isotopes in ice cores and tree rings, like beryllium-10, increase during solar minima when the Sun's magnetic field is weak and doesn't deflect as many cosmic rays. During a grand solar minimum, Earth receives even more cosmic radiation than usual because the Sun's protective bubble, the heliosphere, shrinks. If the Lachamp excursion coincided with a grand solar minimum, Earth would have been hit with a double whammy: weakened magnetic field and weakened heliosphere. The amount of cosmic radiation reaching the surface might have been even higher than from the geomagnetic weakening alone. The Cooper team's climate models, incorporating both effects, suggested that the combination could have caused significant changes in atmospheric circulation, particularly in the stratosphere and upper troposphere. These changes might have altered weather patterns, bringing more storms to some regions, droughts to others, and generally increasing climate variability. They also pointed to evidence from cave stalagmites in the Middle East and China that show changes in rainfall patterns around this time, and to ice core records that show shifts in atmospheric circulation. However, as mentioned earlier, other scientists have questioned whether these climate changes were as severe as the Cooper team suggested. The Greenland ice cores, which provide a detailed record of temperature and snowfall in the North Atlantic region, don't show a major climate shift at 42,000 years ago. There's no obvious cooling or warming event, no dramatic change in snowfall patterns. This suggests that if the Lachamp event did affect climate, the effects were regional rather than global, and perhaps relatively subtle. So, what can we say for certain about the Lachamp event? We know it happened. Multiple lines of evidence confirm this. We know the magnetic field weakened dramatically, to as low as 6% of current strength for a few centuries. We know the poles wandered chaotically, with brief periods where the polarity was actually reversed. We know cosmic ray flux increased significantly, producing more carbon-14 and beryllium-10. We know these changes would have affected the upper atmosphere, producing more auroras, more ionization, and potentially affecting the ozone layer. What we're less certain about is how these changes affected the surface environment and, by extension, life on Earth, including human populations. The direct radiation exposure from increased cosmic rays would have been modest, well within the range that humans and other organisms can tolerate. You'd have to spend a lot of time exposed to get a significantly increased radiation dose, and most people then, as now, spent much of their time sheltered. The UV radiation increase from ozone depletion would have been more noticeable, but again, not catastrophic. People might have gotten sunburned more easily, might have learned to cover their skin or seek shade during midday, but this wouldn't cause mass mortality. The climate effects, if they occurred, might have been the most significant, but as we've seen, the evidence for major climate disruption is ambiguous. What seems most likely, based on current evidence, is that the Lachamp event was noticeable, that it would have been observed and remarked upon by any humans alive at the time, but that it wasn't apocalyptic. It was a disruption, a period of stress, a time when the familiar rhythms of nature were disturbed. For people living through it, the auroras would have been awe-inspiring and possibly frightening. The strange behavior of animals that relied on magnetic navigation would have been confusing. There might have been more storms, more lightning, unusual atmospheric phenomena, and the experience might have been passed down in stories, in myths, becoming part of the cultural memory of those populations. But directly proving this connection between the geomagnetic event and human cultural changes remains challenging, and is likely to remain so until we develop better methods for correlating geological and archaeological records with high precision. Biological and atmospheric effects when the shield falters. Let's think more carefully now about the biological and atmospheric effects of a geomagnetic excursion or reversal. When Earth's magnetic field weakens, what actually happens? How does life respond? First, let's be clear about what doesn't happen. The magnetic field doesn't vanish entirely. Even during the weakest phase of the Lachamp event, When the field dropped to 6% of its current strength, that's still a magnetic field. It's still providing some protection. More importantly, Earth's atmosphere is an incredibly effective shield against radiation, even without a magnetic field. The atmosphere is thick, dense, full of atoms that absorb and scatter incoming particles. By the time cosmic rays make it through the atmosphere to the surface, they've lost most of their energy. This is why, even during geomagnetic excursions, life on Earth doesn't get fried. The atmosphere does the heavy lifting when it comes to radiation protection. The magnetic field helps, certainly, but it's not the only thing standing between us and the harsh radiation environment of space. That said, changes in the magnetic field do affect how much radiation reaches different parts of the atmosphere and surface. Cosmic rays are primarily protons and atomic nuclei traveling at nearly the speed of light. When they hit Earth's atmosphere, they collide with air molecules, producing showers of secondary particles, neutrons, muons, pions, gamma rays. Some of these secondary particles make it to the surface. The intensity of this cosmic ray bombardment varies with latitude. At the poles, where magnetic field lines dip down toward the surface, particles can penetrate more easily. At the equator, where the field lines are horizontal, there's more deflection. During a normal period, with a strong dipole field, cosmic ray intensity at the equator is relatively low and increases toward the poles. During a geomagnetic excursion, this pattern changes. The field becomes weaker everywhere, so cosmic ray intensity increases globally. But more dramatically, the field becomes more complex, with multiple poles and regions of weak fields scattered across the surface. This means that cosmic ray intensity might become highly variable geographically. Some regions might actually see less cosmic ray exposure if they happen to be under a localized strong field patch. Other regions might see much higher exposure if they're under a weak field or near one of the temporary poles. Auroras, which occur when charged particles from the sun follow magnetic field lines down into the atmosphere and collide with air molecules, creating light, also spread to lower latitudes. During normal times, auroras are confined to rings around the magnetic poles, roughly above 60 degrees latitude. During geomagnetic disturbances, the aurora zones expand. During a major excursion, auroras might be visible from the tropics. Imagine living in what is now Egypt, or India, or central Mexico, and suddenly seeing shimmering curtains of green and red light filling the night sky. You'd have no framework for understanding what you were seeing. It would be a prodigy, a wonder, possibly a terror. Auroras are mentioned in myths and legends from high-latitude cultures. The Norse saw them as the armor of the Valkyries reflecting light. The Inuit saw them as spirits playing ball with a walrus skull. The Sami saw them as the souls of the dead. But low-latitude cultures don't have traditional aurora legends because they don't normally see auroras. If they did see them during a geomagnetic excursion, they would invent new explanations, new stories, and those stories might get passed down in altered form. The atmospheric chemistry effects of increased cosmic rays are more subtle but potentially significant. Cosmic rays produce ionization in the upper atmosphere, creating free electrons and ions. This affects the chemistry of the stratosphere and mesosphere, the layers of atmosphere above where we live and breathe. One particularly important effect is on the ozone layer. Ozone, O3, forms in the stratosphere when UV radiation from the sun splits oxygen molecules, O2, and the freed oxygen atoms combine with other O2 molecules. Ozone absorbs UV radiation, protecting the surface from its harmful effects. But ozone can also be destroyed by certain chemical reactions, particularly those involving nitrogen oxides, NOx, and hydrogen oxides, HOX. Cosmic rays produce these compounds by ionizing nitrogen and water vapor in the upper atmosphere. During a geomagnetic excursion with higher cosmic ray flux, more NOx and HOX are produced, which could lead to more ozone destruction and a thinner ozone layer. The Cooper et al. Models suggested that during the Lachamp event, ozone levels could have dropped by a few percent globally. This would lead to increased UVB radiation at the surface, the wavelengths that cause sunburn and skin cancer. For humans, a modest increase in UV exposure would be noticeable, but not immediately catastrophic. People living at high altitudes or low latitudes, where UV is already intense, would be most affected. They might develop more skin problems, might have to adjust their behavior to avoid peak sun hours. Over generations, populations exposed to higher UV might develop darker skin pigmentation as a protective adaptation. But this is evolution on timescales of thousands to tens of thousands of years, not something that happens within a single geomagnetic excursion. For other organisms, the effects might be more varied. Phytoplankton in the ocean, which form the base of the marine food web, are sensitive to UV radiation. Increased UV could damage these microscopic organisms, potentially affecting the entire ocean ecosystem. Plants on land might also be affected, with UV-sensitive species suffering more damage to their DNA and photosynthetic systems. But plants have various protective mechanisms, pigments, leaf structures, that help them cope with UV, and most would likely adapt. For animals, especially those that spend a lot of time in the sun, increased UV could cause skin and eye problems. But again, most animals have protective coverings, fur, feathers, scales, or behaviors seeking shade, being active at night, that would help them cope. One group that might be significantly affected is migratory animals that use Earth's magnetic field for navigation. Many birds, sea turtles, salmon, whales, and even some insects can sense the magnetic field and use it to orient themselves during long journeys. During a geomagnetic excursion with a weak, chaotic field, these animals would become disoriented. Birds might fly in the wrong direction, failing to reach their traditional breeding or wintering grounds. Sea turtles might wash up on the wrong beaches. Salmon might not return to their natal streams. For human hunter-gatherers who depended on these migratory species, this disruption would be serious. If the caribou herds don't arrive when expected, or if the salmon runs fail, people go hungry. There's some indirect evidence that animal behavior did change around the time of the Lachamp event. Studies of cave bear and other megafauna remains from Europe show shifts in distribution and possibly in population numbers around this time. But whether these shifts were caused by the geomagnetic excursion, by climate change, by human hunting pressure, or by some combination, is impossible to say. One more biological effect worth considering: mutation rates. Cosmic rays, when they strike DNA molecules, can cause damage. Mutations. Most mutations are harmful or neutral, but occasionally they're beneficial, providing raw material for evolution. If cosmic ray flux increased significantly during a geomagnetic excursion, would mutation rates increase? Would evolution speed up? The answer is probably not significantly. The increase in cosmic ray flux during the Lachamp event, while measurable, wasn't huge. Mutation rates might have ticked up slightly, but not enough to have major evolutionary consequences over the relatively short duration of the excursion. That said, if a population was exposed to higher radiation for generations, and if that radiation caused increased reproductive mutations, there could be subtle evolutionary effects. Populations might develop better DNA repair mechanisms or other adaptations to radiation exposure. But again, we're talking about subtle effects over long timescales, not dramatic changes within a single excursion event. So, to summarize the biological effects: direct radiation exposure, modest increase, not catastrophic. UV radiation, noticeable increase due to ozone depletion, would require some behavioral or protective adaptations. Auroras, dramatic expansion to low latitudes, psychologically impactful but not biologically harmful. Animal navigation, significant disruption for species that use magnetic navigation, affecting hunting and fishing success for humans. Atmospheric chemistry, changes in upper atmosphere, potential climate effects, magnitude debated. Evolutionary effects, minimal over the short term of an excursion. Overall, a geomagnetic excursion is not an existential threat to life on Earth. Earth has experienced hundreds of reversals and excursions over its history, and life has sailed through all of them. The fossil record doesn't show mass extinctions associated with geomagnetic events, but that doesn't mean excursions are irrelevant to human history. Even modest environmental changes can have significant impacts on human societies, especially small, widely dispersed hunter-gatherer populations living close to the edge of subsistence. A few bad hunting seasons, a few crop failures for populations that were beginning to cultivate plants, a few generations of increased infant mortality due to UV exposure, these could be enough to cause population declines, force migrations, or drive cultural changes. And the psychological impact of seeing the sky behave in strange and frightening ways should not be underestimated. Humans are meaning-making creatures. We need to explain what we see, and when we can't explain it through everyday experience, we turn to the supernatural. A geomagnetic excursion would be a time of portents and omens, a time when the boundary between the natural and supernatural seemed thin, a time when shamans and spiritual leaders would gain influence by claiming to understand or control the forces at work. This cultural response to an environmental stressor might leave more traces in the archaeological record than the stressor itself. Changes in ritual practices, new types of art or artifacts, evidence for increased social hierarchy or religious authority. Modern understanding and future risks. What lies ahead? Let's shift our perspective now from the deep past to the present and near future. What is Earth's magnetic field doing today? And what might happen if another excursion or reversal were to begin? The honest answer is that we don't know when the next reversal will start. Reversals don't follow a predictable schedule. The statistical average of one every 300,000 to 400,000 years is just that, an average. Some periods go much longer between reversals. Other periods see reversals cluster together more frequently. Our current magnetic polarity, the Brunhes normal epoch, has lasted 780,000 years. That's longer than the average, which has led some people to speculate that we're overdue for a reversal. But there's no cosmic clock counting down to the next flip. The geodynamo in Earth's core is a chaotic system, and chaos is inherently unpredictable. The next reversal might begin tomorrow, or it might not happen for another million years. What we can say is that Earth's magnetic field is changing right now. Over the past 200 years, the overall strength of the magnetic field has decreased by about 9%. That might not sound like much, but it's a measurable and sustained decline. More dramatically, the North Magnetic Pole is accelerating. For most of the 20th century, it wandered slowly across northern Canada at a pace of about 10 kilometers per year. But starting in the 1,990 seconds, it sped up. By 2020, it was moving at about 50 to 60 kilometers per year, racing across the Arctic Ocean towards Siberia. This rapid pole movement has practical consequences. Airports, for instance, need to update their runway designations, which are based on magnetic headings. Navigation systems need to be recalibrated. Compasses become increasingly unreliable. For the general public, these changes are mostly invisible, managed behind the scenes by geophysicists and engineers. But they're a reminder that the magnetic field is restless, always in motion. There's also the South Atlantic anomaly, a region of unusually weak magnetic field stretching from South America to Southern Africa. In this region, Earth's magnetic field is about 30% weaker than the global average, and it's been weakening further over time. Satellites passing through the South Atlantic anomaly are exposed to higher radiation levels, which can damage their electronics. Astronauts on the International Space Station receive higher radiation doses when the station passes through this region. Some scientists have speculated that the South Atlantic anomaly might be a precursor to a reversal, a sign that the magnetic field is becoming unstable. During reversals, we often see multiple regions of weak field and anomalous polarity before the global field flips. But other scientists caution that anomalies like this can wax and wane without leading to a reversal. The geodynamo is complex, and not every fluctuation signals a major change. So, what would happen if a reversal did begin in the near future? For modern technological society, a geomagnetic reversal would be much more disruptive than it would have been for our Stone Age ancestors. We rely on satellites for communication, navigation, weather forecasting, and military operations. During a reversal, with a weakened magnetic field, satellites would be exposed to more radiation from solar storms and cosmic rays. This could shorten their operational lifetimes, cause more frequent malfunctions, and require more shielding and hardening. The Global Positioning System, GPS, which is used by everything from smartphones to aircraft to farm equipment, might become less reliable if magnetic field fluctuations affect signal transmission, or if satellites start failing more frequently. Power grids are also vulnerable. During geomagnetic storms, which are caused by solar activity interacting with Earth's magnetic field, electrical currents can be induced in long-distance power lines, potentially causing blackouts. If the magnetic field is weak and chaotic during a reversal, these geomagnetically induced currents might become more common or more severe. In 1859, during the Carrington event, a powerful solar storm created auroras visible as far south as the Caribbean and induced currents strong enough to set telegraph offices on fire. If a similar storm happened today, with our much more extensive electrical infrastructure, the damage could be catastrophic, potentially causing widespread, prolonged blackouts. Now imagine that happening not as a rare event, but repeatedly over decades or centuries during a prolonged reversal. The economic and social disruption would be significant. Aircraft flying at high altitudes, especially over polar routes, would receive higher radiation doses during a reversal. Pilots and flight attendants might face increased cancer risk from cumulative radiation exposure. Airlines might need to alter routes to minimize exposure, increasing flight times and fuel costs. For ground-level residents, the radiation risk would be much lower. Earth's atmosphere is very effective at shielding against cosmic rays. Even with a completely absent magnetic field, the atmosphere would still block most of the radiation, but there would be some increase in surface radiation, especially at high altitudes and high latitudes. People living in places like Denver, La Paz, or Tibet might need to take additional precautions. Increased UV radiation from ozone depletion might require more use of sunscreen, protective clothing, and sunglasses. The psychological and social effects are harder to predict. In our scientifically literate age, we understand what geomagnetic reversals are and why they happen. We wouldn't interpret auroras in unexpected places as divine omens, though some people certainly would. But there would still be anxiety. News media would run alarming stories. Social media would be full of speculation and misinformation. Some people would stockpile supplies, move to supposedly safer locations, or adopt survivalist lifestyles. Governments and scientific institutions would need to provide clear, accurate information to prevent panic. This communication challenge would be significant, especially given the uncertainties involved. Scientists couldn't say exactly when the reversal would complete, how long it would last, or what the precise effects would be. That said, a geomagnetic reversal is not an extinction-level event. It's not even close. Life has survived hundreds of reversals. Human civilization would survive too. We would adapt. Engineers would harden our technology. Policies would change to protect workers exposed to radiation. Navigation systems would switch from magnetic compasses to other technologies, which is already happening. GPS doesn't rely on the magnetic field, and gyroscopes can provide orientation without reference to magnetism. The economic cost would be significant, potentially in the hundreds of billions or even trillions of dollars, but it would be spread over decades or centuries, giving society time to adjust. In some ways, a future reversal might even be scientifically fascinating. For the first time in human history, we'd have the tools to study a reversal in real time, with satellites measuring the changing magnetic field, with ground-based instruments tracking radiation levels, with comprehensive weather and climate monitoring. We'd learn an enormous amount about how Earth's geodynamo works, about how the magnetic field interacts with the solar wind, about how life and technology respond to these changes. And perhaps, by studying the reversal, we'd gain insights that would help us understand the past, including the Lashump event and its potential effects on our ancestors. What if scenarios, reversals during civilization. Now let's engage in some speculative what if thinking. What if a geomagnetic reversal had happened not 42,000 years ago, when our ancestors were hunter-gatherers, but more recently, during the historical period, when complex civilizations existed? Imagine a reversal occurring, say, 5,000 years ago, during the Bronze Age, when writing had been invented, when cities existed in Mesopotamia, Egypt, the Indus Valley, and China. The first signs would be subtle. Compasses, if they existed, they didn't in most places, not yet, would begin to behave strangely, pointing in slightly different directions each year. Sailors navigating by the stars would notice nothing amiss, since stellar navigation doesn't depend on the magnetic field. But as the reversal progressed, strange things would start happening in the sky. Auroras would begin appearing at latitudes where they'd never been seen before. In ancient Egypt, in Sumeria, in the cities of the Indus Valley, people would see shimmering curtains of light dancing across the night sky. How would they interpret this? In Egypt, where the gods were intimately connected with celestial phenomena, the auroras might be seen as the gods themselves manifesting in the sky. Priests would consult their sacred texts, perform rituals, make sacrifices to appease whatever divine force was disturbing the heavens. In Mesopotamia, astrologers would scramble to interpret these new omens. The appearance of unusual lights in the sky would be seen as portents of great changes, the rise or fall of kings, impending war, famine, or flood. In China, where celestial events were carefully recorded and interpreted as reflections of the emperor's virtue, the appearance of auroras might be seen as a sign that the emperor was losing the mandate of heaven, that the cosmic order was disrupted. Scribes would write about these events. They would be recorded in temple inscriptions, in royal annals, on clay tablets, and oracle bones. And here's the tantalizing part. We might actually have these records. We might be able to find them if we knew what to look for. Ancient astronomical texts do mention unusual celestial phenomena: comets, meteors, eclipses, guest stars, supernovae, or bright novae, and occasionally strange coloured lights in the sky. Some of these descriptions might be auroras observed during periods of strong solar activity, which can push the aurora zones to lower latitudes even without a geomagnetic reversal. But could some of them be descriptions of auroras during a geomagnetic excursion? The problem is that we don't have any known geomagnetic excursions during the historical period. The most recent excursion, the Mono Lake event, occurred around 34,000 years ago, long before writing was invented. Unless there was a much smaller, previously undetected excursion sometime in the last 5,000 years, which is possible but not supported by current evidence, we don't have a historical reversal to correlate with ancient texts. But the exercise is still valuable because it helps us think about how civilizations would respond to and record such events. Now imagine a reversal happening not in antiquity, but in the modern era. Let's say it started in 1950, and we're now, in 2024, 74 years into a centuries-long transition. The weakening magnetic field would have been noticed immediately by geophysicists. Monitoring stations around the world measure the field continuously, and any significant change would be detected and published. By the 1960 seconds, as the reversal progressed, it would be clear that something unusual was happening. Scientific papers would proliferate, conferences would convene, governments would fund research programs to understand and predict the effects. The general public would become aware of the reversal through news reports. There might be initial alarm, but most people's daily lives would continue relatively unchanged, at least at first. As the reversal progressed and the field continued to weaken, effects would become more noticeable. Auroras would spread to lower latitudes, becoming common sights even in temperate zones. This would be a boon for aurora tourism, but might also cause concern about what it signified. Compass navigation would become increasingly unreliable. Ships and aircraft would rely more on GPS and gyroscopic systems. Hikers and orienteers would need to learn navigation techniques that don't depend on compasses. Satellite operators would report more frequent malfunctions and would need to replace satellites more often as radiation damage accumulated. Insurance costs for satellites would increase. Launch rates might increase to maintain services. Power grid operators would invest in infrastructure to protect against geomagnetically induced currents, installing devices to block or divert these currents before they cause damage. Airlines would monitor radiation exposure for crew members more carefully, possibly reducing flight hours for individual crew or avoiding high-altitude polar routes during solar storms. Biologists would study whether increased cosmic radiation was affecting wildlife, particularly migratory species. If animals did show signs of disorientation or population declines, conservation efforts might increase. Public health authorities would monitor for any increases in cancer rates, particularly skin cancers from increased UV radiation. Sunscreen use might increase. Recommendations for outdoor activities might change. All of these changes would be manageable. They'd require investment, adaptation, and coordination, but modern civilization is good at those things. We'd cope. The bigger challenge might be psychological and social. A geomagnetic reversal would be a slow-moving crisis, unfolding over decades or centuries. Maintaining public attention and political will over such a long time span is difficult. There would be debates about how much to spend on protection and mitigation, about whether the threat is being overhyped or underestimated, about how to balance the costs of action against the costs of inaction. Some people would deny the reversal was happening at all, or would claim it was natural and nothing to worry about. Others would predict apocalyptic consequences and advocate for extreme measures. Finding the middle path, the rational response based on the best available science, would require effective science communication and strong institutions, qualities that are not always present in modern societies. But overall, humanity would get through it. A geomagnetic reversal is not the end of the world. It's a change, a challenge, something that requires adaptation. And humans are very good at adapting. The question that haunts us tonight, though, isn't whether modern humans could survive a reversal. It's whether ancient humans did survive one, and whether it changed them in ways we can still detect. Closing reflections, memory in stone and story. We're nearing the end of our journey now, this long drift through time and magnetism, through the deep past, when our ancestors huddled in caves and watched the sky with wonder. Let's step back and consider what we've learned and what remains mystery. We know that Earth's magnetic field reverses. This is fact, written in stone, locked in lava flows and sediment layers around the world. We know that the most recent full reversal happened 780,000 years ago, before modern humans existed. But we also know that geomagnetic excursions, shorter and less complete than full reversals, happen more frequently, and we know that at least one major excursion, the Lachamp event, occurred approximately 42,000 years ago, when modern humans definitely existed and were spreading across the world. We know that during the Lachamp event, Earth's magnetic field weakened dramatically to as low as 6% of its current strength. We know the poles wandered chaotically. We know cosmic radiation increased, auroras spread to low latitudes, and the atmosphere's chemistry changed in measurable ways. What we don't know for certain is how these changes affected human populations. Did the Lachamp event cause climate changes severe enough to force migrations or alter subsistence strategies? The evidence is ambiguous. Did increased radiation have biological effects? Probably modest ones, if any. Did people notice the changes? Almost certainly, yes. The auroras alone would have been impossible to miss. Did these observations shape their cultures, their myths, their art? Possibly, but proving this is extremely difficult. And here's the deeper question that lingers. Even if we can't prove a direct causal connection between the Lachamp event and specific cultural changes, is the correlation interesting enough to keep investigating? I would argue yes, for several reasons. First, it reminds us that human history is not separate from Earth history. We evolved on this planet, We're shaped by its environments, its climate, its geology. The forces that move continents and reverse magnetic fields also affect us, however indirectly. Second, it opens up new ways of thinking about the archaeological record. Instead of looking only at stone tools and bones, we can also look at the broader environmental context, including factors like geomagnetic field strength that normally go unnoticed. Third, it might help us interpret myths and legends in new ways. If ancient peoples witnessed and recorded in oral tradition or early writing unusual celestial phenomena during geomagnetic excursions, recognizing this might help us date events, understand cultural diffusion, or identify periods of environmental stress. Fourth, it prepares us for the future. If a reversal does happen in our lifetimes or our descendants' lifetimes, understanding what happened during past reversals will help us predict and mitigate the effects. And finally, it's just fascinating. The idea that the very fabric of Earth's protective shield can falter, that the North Pole can become the South Pole, that the invisible forces we take for granted are actually restless and changing, this is the kind of deep, unsettling knowledge that makes us see the world differently. When you look up at the night sky now, you might notice the stars, the moon, the occasional satellite, but you might also think about the invisible magnetic field arching overhead, that silent guardian that has protected life on Earth for billions of years. And you might wonder, is it stable? Is it strong? Or is it, even now, beginning the slow, chaotic dance that will flip its poles and plunge us, for a time, into a world our ancestors once knew, a world where the sky blazes with impossible lights and the compass points nowhere at all? The evidence from the Lachamp event and other geomagnetic excursions suggests that even if a reversal happens, we'll survive. Life is resilient. Humans are adaptable. The geological record shows no mass extinctions associated with reversals. But survival is not the same as thriving. Even modest environmental stresses can cause hardship, suffering, cultural disruption. For populations living at the margins, for societies already under pressure from other factors, a geomagnetic excursion might be the additional stress that tips the balance. Perhaps this is what happened 42,000 years ago. Perhaps the Lachamp event didn't cause the extinction of Neanderthals or megafauna, but it contributed to it, an extra pressure on top of climate change and competition from modern humans. Perhaps it didn't create cave art, but it inspired it by filling the sky with wonders that demanded to be recorded, remembered, honoured. Perhaps it didn't reshape human history in obvious, dramatic ways, but in subtle ways, nudging populations in certain directions, sparking innovations, testing resilience. Or perhaps its effects were even less noticeable than that. Perhaps it was simply a strange time that passed and was forgotten, preserved only in the chemical signatures of tree rings and ice cores, waiting tens of thousands of years for scientists to rediscover it and puzzle over its meaning. We may never know for certain. The past is elusive. Human memory is short. Stone and bone preserve only fragments of what once was. But the question remains worth asking. What if Earth's magnetic poles flipped during human history, not as a catastrophe from myth or Hollywood, but as a real geological process that our ancestors witnessed and survived? The answer is, they probably did. And if they did, then somewhere in our collective past, buried in the stories we tell ourselves about who we are and where we came from, there might be echoes of that time, memories of when the sky went wild and the world seemed to be ending but wasn't. And perhaps, knowing this, we can approach the future with a bit more humility, a bit more respect for the forces we don't control, and a bit more confidence in our ability to endure whatever changes the restless Earth has in store for us. The magnetic poles will flip again. It's not a matter of if, but when. When they do, humanity will face a test, not of survival perhaps, but of adaptation, resilience, and wisdom. And we can take comfort in knowing that we're not the first to face this test. Our ancestors, 42,000 years ago, stood under strange skies and kept going. They painted on cave walls, told stories around fires, raised children, and built the foundation of everything that came after. If they could endure it, so can we. Thank you for joining me on this journey through deep time and invisible forces, through the mysteries of Earth's magnetic field and the shadows of human prehistory. If this story resonated with you, if it made you see the world a little differently, I'd be grateful if you'd share it with others who might appreciate it too. And as you drift off to sleep tonight, imagine those ancient skies, lit not with the familiar stars, but with dancing curtains of auroral light, green and red and violet, rippling across the darkness. Our ancestors saw them. They marveled, they wondered, and they survived. Rest well. The magnetic poles may wander, but morning always comes.